Okay, let's start. First of all, let's recall whatever I did yesterday for a few minutes. Particularly, I realized that some of the letters which I wrote little smaller, and therefore I can. Therefore, this is a setup. You have a set A contained in Z over P set, whose cardinality is N, which is 0.318p, and it is Sumfree. Then aim, it is in the middle 1/3. When I say it is in the middle, as I explained yesterday, a certain dilation would be in the middle. The middle means 0.318 to whatever it is, p minus 0.318p. Okay, the first thing which we did is essentially make these things into, these two statements into Fourier, and the first statement and then of course we removed t is equal to 0 and then go modulo the equivalence relation x is equivalent to minus x to make life easier, to give you the following, that t in t mod a hat t square is equal to 0.014t. Yes. 0.1084. And the same argument gives essentially that t belonging to t mod a hat t whole square into real part of a hat t equal to minus 0.016p cubed. Oh, the t again. Okay. What I do is I take this z over p z and I remove 0 and go modulo the equivalence relation. Equivalence relation is x is equivalent to minus x. Therefore, if I take x, I don't take minus x, and that is perfectly allowed because a hat of minus t is the conjugate of a hat t. Since a hat of minus t is the conjugate of a hat t, I can combine t and minus t.
This was 4.8, right?
Sorry?
1048.
4.8. Yeah. And from these two equations, we want to get the maximum of a hat t to be a lower bound, and the trivial lower bound is 0.0148. But then this idea of the lobe gives essentially that maximum of a hat t is bigger than or equal to 0.152p, and that's where we start. And as I was telling yesterday, this as well as I can assume that a hat 1 is bigger than or equal to 0.152p for the simple reason that dilation is always allowed, and a hat t is the same as a hat 1 up to a dilation. And now what is the advantage of this a hat 1? There is a theorem of Lev which says that then if a hat 1 is too large, then there is lot of points on one half circle. Okay, and in fact it says essentially that one half circle contains at least n over 2 plus p over 2 pi arc sine mod a hat 1 sine pi over p points. This number which I call m, and therefore now going to my model, there is a half circle containing m points and m is bigger than or equal to 0.238p. Okay. Therefore, you have a number of points, 0.238p points are there, and then we stopped with the assertion essentially that if you have those many points and you have an interval, and then if you add those points to itself, okay, or you subtract, it doesn't really matter what you say, and when you subtract, that number is rather large unless the interval is rather very small. And therefore, that's a theorem which we want to next. And therefore, let me state that. If A, should not use the same A, but it's okay, is contained in 0L, and if 0 belongs to A, L belongs to A, and the cardinality of A is equal to M, then A minus A is in cardinality is bigger than or is equal to the minimum of L plus M and 3M minus 3. Okay? And now I have to discuss two cases, which one depends upon the minimum. Therefore, now let's look at the, see, one thing which we know already, that this A minus A is contained in A complement, because A is Sumfree. Since A is in Sumfree, that A minus A cannot have an intersection with A. And therefore, in particular, cardinality of A minus A is less than or is equal to P minus N. And recall, so this is what I wanted, but I wrote so small. Okay, and therefore now we discuss two cases. Case 1, 3m minus 3 is minimum. In case 3 minus 3 is minimum, that would mean essentially the cardinality of A minus A is bigger than or is equal to 3m minus 3. On the other hand, this cardinality is less than P minus N, because A minus A is contained in A complement. Since A minus A is contained in P complement, and this obviously leads to a contradiction because M is at least 0.238 and N is 0.318, and that leads to a contradiction immediately. And therefore, this case does not arise. Therefore, we conclude L plus M is minimum and cardinality of A minus A is less than or is equal to L plus M. Greater than or equal to L plus M. Sorry?
3m minus L plus M?
3m minus 3, yes. L plus M is less than 3m minus 3 and the cardinality of A minus A is bigger than or equal to L plus M. Yes?
Little n is
0.31, that is the cardinality of A.
and m is also
M is, okay, let's say, little n 0.318 is the cardinality of A. And this little m is at least, little m is in a half circle and maximum with respect to that property.
M is within this, the surface is half a circle.
Half a circle. M is, yeah, that's what I'm writing, M to be 0.238, and half a circle contains M, which is 0.238. And this is the maximum with respect to property. I take that half circle which contains lot of points, and that half circle has M points, which is M is at least 0.238. Is it okay? And now on the other hand, this gives you less than or equal to P minus E. Again, as usual, P minus N. And that gives you L less than or equal to P minus N minus M. There may be some constant slope, correct. Okay, and that number turns out to be, at least for the small values of N, this turns out to be 0.444. Therefore, what we have proved is that even though there are M points on the half circle, but these M points on the half circles are not really spread throughout. They seem to lie in an interval of length 0.444.
The unit is P.
Sorry? P unit is P. Yes. Yeah. Yes? Yeah. Correct? You correct? Okay. So, oh, sorry. Therefore, let me start writing here so that people can easily do. For the lowest value of M. I mean, yeah, that part of the blackboard is probably difficult for you to read, and therefore let me not write that. Okay, that's where. Therefore, now we have got in an half circle, and even not in an half circle, even within the sink, essentially 0.238 elements sitting inside 0.444. Good. Now we go to section 2. Where we now change the track. Okay? Now we are going to do combinatorics. And this combinatorics is what is called exclusive zones. What does it say? It says that if some A1 lies and A2 lies in A, then A1 plus A2 cannot lie, A1 minus A2 cannot lie. Therefore, the existence of every element excludes the existence of few other elements. And this combinatoric, we want to really put it more carefully. It's okay? And that's a combinatorics which we want to do. Is that what I have to do? Yes. Therefore, let me write that. Okay, you see, mostly I will be starting on A minus A rather than A plus A. The advantage of A minus A is that if I prove a certain theorem for A, then the same theorem holds good for the translation of A also. If you, for A equal to 0 to L, if I prove, then for A is equal to U to U plus L, the same thing holds, because as far as A minus A is concerned, whether A is 0 L or U to U plus L, it won't make a difference. Correct? And therefore, whatever theorem I am proving, I will always assume A contained in 0 L, etc., but I will prove results on A minus A. But this A minus A results would actually work for this part also, which is a part which I am calling A0. Therefore, let's just define it. A is equal to A0 union A1.
We have no idea where is A0.
Yeah, exactly. That's why. But on the other hand, there are strong reasons to expect that it will be in the left half of the circle. Because ultimately that's what even we are going to prove. That is going to be between -318 to this. Okay, therefore let's write this A0 union A1, where A0 is the part in the big half circle. Of course, when you say half cycle, there cannot be a big half cycle and a small half cycle. But on the other hand, by big half cycle, I mean that half cycle which is really has a lot of elements, and a small half cycle is one which has a few elements. And therefore, this is my A0. Whatever is in this half circle is my A0. And even whatever is there in my half circle, which is the A0, actually lies not completely spread, but on the other hand, over an interval of length L, somewhere, where L is around 0.444. Okay. Now let me state a few theorems on the exclusion zone. Good. Before I go wrong, let me. Therefore, I have the same setup. A is contained in 0L. Cardinality of A equal to M. Then if L plus 1 is less than 2k minus 1 divided by k times M, then minus M over k minus 1 and M over k minus 1 is contained in A minus A. And this result is classical, and therefore I won't bother to prove that. Okay? And therefore, whatever is contained in A minus A cannot be in A, because it is, therefore, this whole interval minus M over k minus 1 to M over k minus 1 is excluded, provided L plus 1 is less than 2k minus 1 into M. Yeah, I am going to use it with the A0, of course, because that's what I know, because the A0 is contained in any set of interval of length L and with the cardinality M. Okay? Probably I should have, that's why I said probably I should have used the word B, but that doesn't matter, I can even do that. So that there will be no confusion, and then I can always use with the A0. And the second exclusion zone, if L is lesser or is equal to 2M minus 2, then L minus M minus 1 divided by K and M over K is contained in B minus A. This also I will sort of not prove. Let me prove at least one more result, which is somewhat interesting. Let me just prove at least one result. 2b minus 2m minus L minus 2, 2b plus 2m minus L minus 2 is in the exclusion zone. Therefore, let me at least prove one result. Therefore, let us see how do you prove this result. Okay? Before proving this, let me say what roughly it says. What it says roughly is essentially that let's just say what it says roughly. You are assuming that B belongs to B. Oh, B is Sumfree B. I am going to use it only for A or A0, etc. Therefore, everywhere I have to assume B is Sumfree. No, I don't think so. I mean, B minus B, I don't. This is true generally, but I will use for A0, then something contained in A0 minus A0 cannot be in A. Okay. Now you see B belongs to B. Okay, and suppose if X belongs to B, then x plus b cannot be in B, and x minus b cannot be in B. Therefore, you are fixing a b and then you are fixing an x, and therefore every element would essentially exclude one more element. B is there, it will exclude one more element. Since it excludes one more element, therefore the density of A is expected to be less than half. Because every element of A actually excludes one more element of A, and therefore the density is expected to be half. Okay? But what may happen is theoretically the following. In every interval of length 2b, the first half may be in B, the second half not in B. Then this will be in B, and this will not be in B. If I take this in intervals of length 2b and take the first half in B and the second half not in B, third half in B, fourth half not in B, and if I keep doing that, then the B as a difference will never occur because I have a gap. Therefore, as a difference, B will never occur. Good. And this example shows that the density has to be probably less or equal to around half maximum. But what may happen is at the end of the point, there may be a little bit, and this little bit may be covered by B. Therefore, there's a slight degeneracy. And therefore, a little extra information would tell you that definitely the density has to be less or equal to half. That's basically the idea which I am going to use. I am going to use the idea that if B belongs to B, then every interval of length 2B will contain at most B elements. Correct? That is clear, because if X belongs and X plus B does not belong, and therefore obviously exactly half of them can belong. Therefore, suppose not. Which means that there exists an X in the interval 2a minus lambda to 2a plus lambda, lambda appropriately defined, whatever the lambda is, 2m minus L minus 2, which really belongs to B. Then I want to get a contradiction. Okay, I want to say that all these elements, the whole interval belongs to B minus B is what I want to say. But suppose there is an element which belongs to B, then I want to get a contradiction. Therefore, there are two elements now which belongs to B, I know. X also belongs to B, B also belongs to B, and therefore I have two extra information, X belongs to B, B belongs to B, and therefore I should be able to say that the density has to be less than half. Okay? Therefore, let's see why the density has to be less or equal to half. Okay, where is this? Where did I keep it? Oh. Therefore, what is the setup? The setup is there is a U plus L, therefore there is an interval of length L. This interval of length L has M elements. This interval of length L has M elements, and this L is less or equal to 2m minus 2, and there is a B which is between L by 4 and L by 2, and that existence of that B will make a large portion exclusion zone. In particular, okay, therefore suppose there is an X, and let us assume that this X is bigger than 2a. Now let's do the following. 2b. Take that. u to u plus L, you break it into three parts, I1, I2, I3, where I1 is u to u plus L minus 2b, I2 is that to 2b u plus 2b, and then u to u to L. Because I am assuming L is bigger than 2b, yeah, okay. Okay, now you look at I1 union I2 intersection A. Okay, I1 union I2 is an interval of length 2b. Since it has an interval of length 2b, it can have only b elements of b. Okay, because an interval of length 2b can have only two elements of b. I mean b. No, what's the problem? Sorry. Okay, we know that an interval of, see, b belongs to b. Once b belongs to b, an interval of length 2b can contain at most b elements. It cannot contain more than that. B contains b and then interval of length. And I1 union I2 is an interval of length 2b, and therefore it can contain only b elements. I2 union I3 also is an interval of length b, and therefore that also can contain only b elements. Okay? And now look at I1 union I3 intersection B. I1 is of length L minus 2b. I3 is also length L minus 2b. Therefore, the total length is 2 times L minus 2b. Out of which many elements have to be excluded. Okay, I will tell you what are the elements to be excluded. You look at u and u plus x. U and u plus x both cannot be there because x is in B. Since I am assuming x is in B, u and u plus x cannot be there. And this x being assumed to be bigger than 2b, this u plus x will come and sit in I3. Therefore, this element of I1 excludes an element of I3. Okay? And the same way, u plus 1 will exclude u plus x plus 1. And the same way, u plus L minus x will exclude u plus L. Okay? Therefore, there are L minus x pairs in which one element has to be excluded. And therefore, this number is this. Because the length of the interval minus the number of pairs in which at least one element. And now you can add I1 union U3 intersection B, I2 union I3 intersection B, and I1 union I3 intersection B. And this is precisely 2 times u plus L intersection B. So you take I1 union I2, I2 union I3, I3 union U, that is exactly twice the whole thing. And the total sum now is 2L minus 4B minus L plus X plus 2B and that number is equal to L minus 2B plus X but X is strictly bigger than 2B and therefore this number is strictly less than L. x is, wait, 1 minute, minus 2b plus x, and x is, I'm supposed to get less than L, 1 minute, 2b minus L, this is L minus x, and 2L minus 4b, that is right, minus L plus x plus 2b, and therefore that will give you a 2L minus L will give you an L, and then there's a minus 2b plus x, and what do I want to say? I want to say that this is L so that the density is less than half. I'm getting bigger than x. Just a minute. This is to be right, and then it allows an L minus x elements. Is it L minus x, right? Because u plus x, x is bigger than 2b. U plus x, therefore that's an L minus x elements which are that have to be thrown away because only one element will be there, and that would essentially mean that and the length of the interval is an L minus b here and an L minus b here, L minus 2b here, therefore 2 times L minus 2b, 2L minus 4b minus L plus x, which is L, and x is bigger than 2b. Once x is bigger than 2b, this is slightly bigger, and union at 2 intersection b, this has at most, that excludes b elements, this excludes p elements, and here L minus x elements are excluded. X is, at least for x less than 2b, this argument works for x less than 2b. So the argument should work for x bigger than 2b, u plus L minus 2a, u plus 2a, and let's see, and b is
X minus L elements.
sorry?
Between in the u plus x, or u plus 1, u plus x plus 1, and so on.
Yeah, it is.
Minus x is x minus
L, no, L minus x elements, no?
Yeah.
Yeah.
Yeah, but you wrote L minus x. Plus 1 is
Yeah, yeah. Sorry? Plus 1 is, I mean, u plus L, no, this is u plus L minus x. That's right, no? Therefore, there are L minus x elements, and these L minus x elements are thrown away, and L minus x elements are thrown away, then you see 2b minus 2m minus L minus 2, and I am looking at an element which is bigger than 2b but which is less than 2b plus 2m minus, okay, 1 minute, therefore my x is 2b plus, oh yeah, sorry, you are right. This is less than L minus 2b plus x may be bigger than 2b, but on the other hand, this is the only interval in which I am interested. Good? And therefore, x may be bigger than 2b, but x is less than 2b plus 2m minus L minus 2. These are the only elements which I want to avoid. Therefore, x is bigger than 2b, but less than 2m minus L minus 2. No, 2m minus L plus 2m minus L minus 2. And now the L cancels, B cancels, which is strictly less than 2m minus 2, because as he said, I should have taken a 1 into account. and that gives a contradiction to the original assumption. Because I have to divide by 2, and therefore that means, okay, therefore the number of elements is really m minus 1. And that gives a contradiction to the original. Yeah, essentially you have to play with the fact that there are 2 elements who cannot appear as a difference, b and x, which means that z appears, z plus b cannot appear, z minus b cannot appear, z plus x cannot appear. Therefore, these are the exclusion zones which we want. It's okay? Good. Now with that, what do we do? Now we go to section 3. And now what we want essentially is, what would be the smallest element that would appear in A? And whether we can get some idea about the smallest element that would appear in A. And consequently, I take the following model. That is the model which I take now. Rather than 0 to p, and then define mu to be minimum of mod z appears in A. Okay, and then I would like to know what can I want to say about this A. You have to erase everything because whatever I wanted to keep, I erased. Okay, yeah. Now for whatever I wrote here, let me write it down. That is one thing which we had. One more thing which I want to, here. And one more thing which I want to keep is that L plus M is less than or equal to 3M minus 3, which we proved because the minimum of L plus M and 3M minus 3. And therefore, that gives you an information that L is less than 2M minus 3. And that information also I need. Okay? And now the exclusion zone, which unfortunately I erased, is the following. If L plus 1 is less than 2k minus 1 divided by k times m, then minus m over k minus 1, m over k minus 1 belongs to A minus E. This is one exclusion zone which we wrote. And we will always be using by B to be A naught. Occasionally, once we will be using as A, but that's okay. Okay? This is what we wrote. This is one exclusion zone. And now you put k equal to 3. If you put k equal to 3, I have to verify the condition that L plus 1 is less than or equal to 5 over 2 times m. And L plus 1 is less than or equal to 5 over 2 times m. That condition is automatically satisfied. And consequently, one more result which we have is minus m over 2 to m over 2 is contained in B minus B. Because I take k equal to 3, and therefore we have minus m over 2 to m over 2 contains. This is essentially equivalent to saying this is essentially equivalent to saying that this mu which has been defined here is at least as big as m by 2. Because the minus m by 2 to plus m by 2 does not lie there, and therefore this is at least equal to m by 2. Good. Probably we can do it slightly better. Therefore, let us say, suppose L plus 1 is less than 3 by 2m, then I can even choose k equal to 2, and therefore that will give you a stronger result. Minus m to m itself is contained in b minus b. Okay? So far, so good. Now let me prove another lemma. Suppose mu is bigger or equal to p minus n plus 1 divided by 3, and that number which turns out to be what? 0.227. Suppose up to 0.227 you say that there is no element of A because mu is the smallest element. Therefore, up to 0.227 you are able to say that there is no element of A. Then mu is bigger or equal to 0.318. Therefore, if you somehow can exclude up to 0.227, then you have already got the result which you want. Because I really want the number to be 0.318, and therefore only up to 0.227 I have to exclude. Okay? And in this here I am going to use the fact B is equal to A. Therefore, what is the situation? I have the set A. This set A lies between mu and P minus mu. Because that's what I am assuming, that the least element is mu, and in the absolute value, and therefore that lies between P and mu, and this is where your A lies, and therefore and this A has 0.318 elements. And now I can use the exclusion zone thing. There was another theorem which unfortunately again I erased. It's always a problem with writing a little big, I have to erase, but the theorem essentially says that if m is bigger or is equal, L is bigger or is equal to lesser or is equal to 2m minus 2, then, and for any b which lies between L by 4 and L by 2, 2b minus 2m minus L plus 1, 2b plus 2m minus L plus 1 is A free. That's the exclusion zone which we just proved. Let's see whether I wrote it correctly. 2m minus L plus 1, correct. L plus 2, it doesn't, I don't think, as Professor Desway said, that the O of 1 should make much different. And that is the situation which I am now going to apply. Okay, the L is the length of the interval and M is the number of points. And the length of the interval is P minus 2 mu. And the number of points is N. And I have to check whether the number of length of the interval is less or equal to twice the number of points. Okay? This is the first thing which I have to check is whether the L, which is the length of the interval, which is P minus 2 mu, is less or equal to twice the number of points. But on the other hand, what is it? Therefore, I have to prove that whether 3p minus 6 mu is less than or equal to 6n. 2 times m, yeah. Okay, which means that 3p minus 6 times mu, which is 2p minus n plus 1 is less than or equal to 6n is what I have to check. Six mu is 2. And that essentially means I have a 6n here and a 2n here, and then 3p minus 6 mu is what? And mu is what I have taken. 3 mu is p minus n, and therefore 6 mu is 2 times p minus n. Okay. Therefore, I have to verify whether p is less than or equal to 8n, which is clearly satisfied. Therefore, that condition is satisfied. And consequently, we have a big interval which is sum-free, and that interval again we can write. Therefore, once we have L is less than or equal to 2m minus 1, I want that interval 2b minus 2m minus 2l. Thus, interval is A-free. Let's write what that interval is. I take b equal to mu. I need a point which lies, and mu actually, therefore I take b equal to mu. And when I take b equal to mu, then I get 2 mu minus 2m, okay, whatever the notation, 2 times m is n, and L is p minus 2 mu plus 2, and 2 mu plus 2n minus p minus 2 mu plus 2 is A-free. And you can check actually mu lies in this interval. But mu belongs to A, and therefore that gives you a contradiction. Therefore, from that thing, etc., we prove that if mu is already bigger than 0.227, then we are already happy. Is it okay? I just use this theorem. Therefore, I just take this, because A is already contained in mu to p minus mu. Therefore, mu to p minus u, there is a A which has 0.318 elements, and I just apply that theorem. Therefore, there is a big interval which is A-free, but on the other hand, that big interval contains already mu, and that settles that. Therefore, that is exactly the situation. And now, yes. And now I want to say, that this particular condition is not satisfied. Therefore, that will be the next lemma. I think I'll have time to finish that lemma. Therefore, that's a lemma. If L plus 1 is less than 3 by 2 times m, we are through. Okay? Okay, let's prove that. Why, if L plus 1 equals less than or equal to proof. Suppose L plus 1 is bigger than 3 by 2m, then this statement says that minus m to m is not A-free, is A-free. Since minus m to m is A-free, that already means that your mu is bigger than or equal to m. And given these parameters, this m is easily seen to be bigger than p minus n plus 1 divided by 3. because p minus n plus 1 divided by 3 is only 0.227 and m is 0.284. And once mu is bigger than p minus n plus 1, by this theorem, mu is already bigger than 0.318 and we are happy. And therefore, we can assume, therefore, that's the next assumption which we can make. We can assume that our L is shown here. That's our L plus 1 is bigger than 3 by 2m. That is the situation we are in. Okay? Okay, given all this information, just let me conclude by just stating what is that we have proved so far. What is that we have proved so far is, this is where we will start tomorrow. What we have proved so far is that if I take this as my model for the ZP star, Z over PZ. Therefore, my model starts at minus p by 4, minus m, minus L over m minus 1, minus m by 2, 0, m by 2, L minus m minus 1, m, p by 4 to 3 by 4. If I take this model, then in this model, A has less than or equal to m elements because it is an half circle. And any half circle can have at most m elements. Since any half circle have at most m elements, that has less than or equal to m elements. And then we have already checked mu is bigger than or equal to m by 2. But it's not true m less than m, which means that there are no elements here. And then we proved under certain conditions L minus m minus 1 divided by k, m over k is an exclusion zone. Since L minus m minus 1 over k, m over k is an exclusion zone, take k equal to 1, there are no elements here. Okay, this is where it is. And therefore, only other elements, therefore let us call, there may be elements here, which we will call A1 plus. There may be elements here, which we will call A2 plus. And therefore, this corresponding to the negative things is minus m by 2 to, yeah, this one is A1 minus and minus p by 4 to minus m, A2 minus. Therefore, outside the left half circle where we expect everything to lie. You see, now we are getting even a picture about where this big circle lies. P by 4 to 3 by 4 has at most m elements, and outside there are only few elements, and those 4 elements are concentrated between m by 2 to L minus m minus 1 as well as m to p by 4, and similarly the negative part of it. And these are all the elements. Now we want to say that if all these elements we add, whether we do get 0.318 elements, and we will say that we will not get 0.318 elements, and that's how we will get a contradiction. Good. I think that will stop that, and with this we will start tomorrow.